Hello everyone, and welcome to another exciting GCSE Physics lesson. Today we're jumping into one of the most important ideas in all of physics, conservation of energy. Now, if you've ever wondered how roller coaster rides, swinging pendulums, or bungee jumps work, this concept is at the heart of them all. So buckle up, we're about to explore some thrilling examples and ask you questions that'll get those brain cells buzzing. First things first, what is conservation of energy? It's the principle that tells us energy cannot be created or destroyed. It only transfers from one store to another. Think of it as the universe's ultimate balancing act. If something seems lost, it probably just changed form or moved somewhere else. Imagine you're sitting on a seesaw with a friend. When one side goes up, the other side goes down. Overall, the seesaw's motion balances out. That's a bit like energy in a closed system. It's always accounted for, just in different forms. Next up, what is a closed system? A closed system means no energy flows in or out from the surroundings. The total energy stays the same. If you had a magical pendulum that never lost energy to friction or air resistance, it would keep swinging forever. That's why real pendulums eventually slow down. Some energy goes into warming the air around it, yes, even if we can't feel it, and into sound, that faint swooshing noise. Let's take a moment to picture a roller coaster at the top of a giant hill. At the top, it has a large gravitational potential energy store. It's high up. As it zooms downward, that potential energy transfers into kinetic energy, making it go faster and faster. Some energy also drifts away to heat, from friction on the tracks, and a little to sound, those excited screams you hear. And guess what? Total energy is still conserved. It's just been shifted around from one place to another. Now, imagine a simple pendulum, or even a child on a playground swing, something we can all relate to. At the highest point, there's maximum gravitational potential energy. As it swings down, that energy converts to kinetic. Then, on its way back up, the kinetic energy switches back to potential. This back and forth continues until friction and air resistance gradually slow it down. But if we consider the swing plus the air around it as our system, the total energy hasn't disappeared. Some has just warmed the air or made a gentle whooshing sound. Picture you're at an adventure park where you see a friend strapped to a bungee cord and about to leap off a platform. At the top platform, they have a high gravitational potential energy store. During fall, potential energy transfers into kinetic energy, whoosh. During cord stretching, the bungee cord stores energy elastically as it stretches. During snapback, the cord pulls them back upwards, transferring elastic potential energy back into kinetic, and then again into gravitational potential as they rise. By the time they settle, some energy has been transferred to thermal energy in the cord and air. The cord warms slightly under stress, plus maybe some squeals of excitement, sound waves. The total is still there, just spread out in different forms. All right, my brilliant students. Let's see if you can apply these ideas. Keep your answers short, sweet, or dive in with lots of details. Just post them in the comments below. In our next video, we'll break down the solution step by step, so make sure you stay tuned. You drop a basketball from your head height and quickly catch it halfway down. Describe what energy stores are involved before the drop, during the drop, and at the moment you catch it. Where might some energy go that you haven't thought about? When you pull back on a bowstring, you're storing energy in the bow. Once you release, the arrow soars through the air. Explain how energy is transferred from the moment you start pulling the bowstring to when the arrow leaves the bow. Think of a diver bouncing on a springboard a few times before diving off. Map out the changes in energy stores as the diver bounces up and down and then leaps into the air. How could friction or air resistance affect the total energy in this system? Imagine two small, battery-powered toy cars on a track. Both start at the same time, but one has slightly more friction on its wheels. Predict how this friction difference might affect each car's energy transfers and overall motion. You have a simple catapult made from a stiff rubber band stretched between two posts. You place a small object in the band, stretch it, and release. Describe the energy store changes from the moment you start pulling the band to the moment the object lands on the ground a few meters away. Feel free to come up with your own scenarios, too. The more creative, the better, because energy is everywhere. Conservation of energy means we never lose energy, we only transform it or transfer it. A closed system keeps the total energy the same before and after. Friction and air resistance often lead to a transfer of energy into heat, sound, or other surroundings. By tracking energy stores, gravitational, kinetic, elastic, thermal, etc., you can decode what's really happening in every scenario. That's it for our in-depth look at conservation of energy. If you're enjoying these lessons, hit that like button, subscribe, and ring the notification bell so you don't miss future videos, and especially don't miss our follow-up solutions video, where we'll break down the answers to these practice questions step by step. Now it's your turn. Pick a question, or a few, from the ones listed. Share your answers or any real-life examples of energy transfers in the comments below. I'll see you soon in the solutions video, where we'll explore detailed explanations and make sure you're fully prepared for your GCSE exams. Thanks for watching, and remember, energy may change its form, but curiosity is always conserved.